Good morning, everyone. My name is Qinghua, and it's my honor to give the presentation here today about my work embedding morphine intelligence into architect software optics for real applications. Morphing is a fundamental property of software optics that is what enables their unique functions and natures. Today, I will show you how we draw inspiration from nature to integrate this principle, morphing intelligence across different scales of robotics. As you can see on the slide, on the meter scale, creatures like human reconfigure their body to adapt to different terrains. At organ level, spatial heterogeneity defines an organ's complex and load capability. And down to the tissue level, the active and the passive morphine enable both acquisition and sensing. Inspired by these principles, we have applied these same strategies to robotic design. This allows us to regulate not only configuration and the complex, even control their acquisition and sensing properties. First, I will explain how we were inspired to use flexible structures to achieve morphological reconfiguration. Our goal is the terrain adaptive locomotion, meaning the rover must adapt to different terrains by changing its shape. To achieve that, we explored three structures: a rod band and length structure. However, the band structure, the simple structure is highly flexible, but not stable to hold the wheel direction. And the band structure is stable and strong enough to bear the load and hold its configuration, but is too rigid to be deformed. And the length structure gets a good balance of both the flexibility and also the structural stability. With that, we can change its configuration in different scenarios, such as we can not only swimming or walking on the flat ground, but also we can rolling from the mountain to save energy and overcome different barriers. In the next part, I will introduce how we utilize architect structures to regulate the compliance of soft router arm. As mentioned before, the biological organs like elephant trunk or swan necks, structural heterogeneity gives them a unique combination of compliance, flexibility, and load capability. Inspired by this, we developed an architect structure we call trim the helical. The key advantage of that is by tuning the parameters, we can independently regulate its bending compliance and actual compliance. This allows us to design the soft route arm with customized performance. For instance, we can create a soft compressible trunk arm with excellent interaction, compliance, and delicate tasks. Alternatively, by tuning the parameter differently, we can achieve a structure that is harder to compress but easy to bend. This mimics the property of the swan necks to provide higher flexibility and faster response and stronger load capability. This is particularly crucial for applications like real-time teleoperation, which enhance the performance is essential. And if we expand this architect moving intelligence to smaller scale, such as tissue or structural material level, we can bring more possibilities, such as more complex execution forms. As mentioned previously, biological systems like octopus and elephant exhibit tissues that are more anisotropic and heterogeneous. This inspired us to develop a methodology for introducing high programmability. And this capability enable us to program its material modulus in 6 dimensions and enable us to engineer different organisms, not only soft muscular organs, but also bionic robotic legs with integrated rigid joint. For example, we can realize the soft elephant trunk rod and also rigid elephant leg with the different joint. And it also have very good dynamic performance, such as like working with different joints and kicking balls. In the tissue level, except the execution, we can also introduce sensing regulation when electromechanical coupling effect with flexible electrodes or smart materials. In this smart lattice foam design, the capacity mechanical coupling effect was introduced when flexible electronic layer to realize combined with the tunable mechanical behaviors, we can tune its sensitivity and also realize required impact absorbing performance. And to achieve this co-design of mechanical and functional targets, such as for sensing, the neural network was involved to handle the nonlinear behaviors and discrete and large design workspace. This approach allowed us to successfully embed complexity for sensing into a neat pipe, create a device that provides physical protection from impact while simultaneously detecting the movement. Furthermore, by integrating the 3 sensors in different locations, the system can accurately determine the location of impact and classify different types of physical interaction. Finally, utilizing the architect structures and the materials, we have realized the integration of morphing intelligence from whole body to tissue level. The next step will be the cell level to regulate the interface property that has a significant influence on contacting during grasping, manipulation, and interaction. And the more challenging question is how we handle the integration of all levels and realize the co-design of different functions. And with this expand large design space and complex multiple physical field coupling effect, maybe the machine learning will be the future of the more advanced design. And above is my presentation. Thank you very much for your attention, and I'm happy to answer any questions.